All right, we're on our last focus area objective of the year. It's going to be about momentum. And if you know what momentum is, you might know it in English. Like if you have momentum, things are going good. Like in sports, a team might have the momentum. They've scored a bunch of points. Maybe the game's turning in their favor. But when you're thinking of momentum in science, think of how hard is it to stop an object that's moving. So if an object's coming at you and you have to stop it, is it easier to stop an object that's moving really fast or really slow? Obviously, it'd be easier to stop something that's moving slow. Um, Another way to think of it is, would it be harder to stop something that's moving that's really heavy or really light? Yeah, it would be definitely harder to stop something heavy. So those are the two factors that determine momentum. Momentum is mass times velocity. So the heavier an object is, the more momentum it has, and the faster it's going its velocity, the more momentum it has as well. So something with more momentum is harder to stop if it's moving. I kind of just said this on the last slide, so you can read this for yourself. But again, objects that have more mass or more velocity have more momentum. So here's a little scenario. It says, imagine a bowling ball rolling down the lane. It's going to hit the pins soon. The heavier the ball, the greater the acceleration, and it's going to actually hit the pins harder. You might notice somebody that throws a really light, like a 6 or 7 pound ball, when it hits the pins, they don't move as much because the ball doesn't have as momentum. But when somebody throws a heavier ball, like 14, 15 pounds, the pins really start to move around because the ball had more momentum. And obviously, the harder you throw the ball will add momentum to it as well. So let's think about this. A semi-truck and a small car driving down the street. Both vehicles are moving 25 miles per hour. Which vehicle has more momentum? Explain. Press pause while you think of it. And I hope you said the semi-truck. And remember, if you think of momentum as what's harder to stop, it'd be much harder to stop a semi-truck than a small car. Or what would you rather be hit with? You'd rather be hit with a small car because it has less momentum. Mathematically, we said momentum is mass times velocity. Their velocity is both the 25 miles per hour, so that's the same. So it'd be whichever has more mass, the semi-truck clearly would have more momentum. Question 2 there says the semi-truck stops and parks and the small car keeps moving. Which vehicle has more momentum? Press pause if you need to think. And hopefully you said the car, because something that's stopped has no momentum. Remember, the formula is momentum equals mass times velocity. So if you're not moving, your velocity is 0. So it doesn't matter what your mass is. 0 times whatever mass you have is still 0. So the small car, if it's moving, would have more velocity than anything that's not moving. So a change in momentum, if we're going to gain or lose momentum, takes force and time. To stop an object, we need to apply a force against its motion for a given time. Sometimes friction won't be enough. If we're applying a force against it, like my car is not going to stop until it runs out of gas because the force I'm applying is greater than the frictional force from the road on my tires. But again, the more momentum, the heavier or faster or both that an object has, the harder it is to stop. You need more force or longer time to bring it to a stop. Press pause if you need to put these in your notes. So there's something called the law of conservation of momentum. If you remember back to the law of conservation of energy, that law of conservation of energy said we can't create or destroy energy and the total amount of energy stays the same. Well, all laws of conservation have that same principle, that the total amount stays the same. In this case, the total momentum of all objects interacting with each other stays the same. So if you look at the picture on the left, ball A and ball B collide. They each have their own momentum when they hit. They're both moving. Ball A has momentum. So ball B is sitting there. Ball A hits it. After the collision, ball B is going to move. And it's going to get its movement or momentum from ball A. And if you look at the math over here on the right, we're not going to do the math for momentum, even though it's pretty easy. Before the collision, it said ball A had a certain mass and a certain velocity. You multiply those together, this was its momentum. Ball B, before the collision, had the same mass, but no velocity, so no momentum. Well, if the momentum before the collision is 0.40, total momentum, even though it was all with ball A, momentum after the collision will also be 0.40. So go ahead and press pause if you need to. Put this in your notes. Now we're going to talk about 3 different types of collisions. Collisions mean like a wreck, when 2 things hit each other. In yellow there, highlighted, it says elastic collisions. Elastic, if you remember, is bouncy or stretchy. We had elastic energy, anything that bounces or stretches. And elastic means the two objects that collide or hit each other bounce off each other and move separately. So momentum and kinetic energy, they're still moving, is conserved. Let's take a closer look. We see in picture A, ball 1 here is going to hit ball 2. Since it's an elastic collision, they bounce off each other. Now notice, ball 1 bounces further off of ball than ball 2 does. Ball 2 barely moves at all, but they do both bounce. The total momentum is the same. If we did the math, whatever it might be, this ball has just say 0.5, this ball has 0.7, that's a 1.2 total. And maybe after, this ball has 1.0 and this ball has 0.2. But if we add those together, we'd have the same total momentum. So in elastic, the key to remember for elastic collisions, the objects bounce after they hit each other, and momentum, well, momentum is always going to be conserved, but in this kind of collision elastic, kinetic energy is also conserved. Here's some more. It shows, again, initially at the top, both balls, it says, have the same mass. B is going faster, which you should be able to tell just because it has the longer vector up here, that longer arrow. When they collide, remember, they're going to bounce because this is an elastic collision. The momentum will be the same because we said momentum is conserved or doesn't change. And kinetic energy is going to be conserved, meaning they're both going to move. Now, do they have to move at the same speed? No. This ball, originally ball B had more momentum, so it's going to transfer that to A. So A moves more than B, but the total amount of movement, kinetic energy, and momentum is going to be the same in elastic collisions. Go ahead and throw that in your elastic collision parts of your notes. Press pause if you need to. Inelastic collisions. So elastic, remember, the kind we just talked about, bounce off each other, kinetic energy, and momentum is conserved. Inelastic, the two objects deform, so the total kinetic energy changes. Look at the picture over here. Neither of these balls looks the same. The shape of them actually changed. They kind of bent in. The objects do move separately, but in this case, only momentum is conserved. So elastic, they bounce, move separately, and we conserve momentum and kinetic energy. Inelastic, they still bounce, but they change shape, so kinetic energy is no longer conserved. That's the difference. Momentum is conserved. Elastic conserves both kinetic and momentum. Inelastic, only momentum. There's something called perfectly inelastic collisions, and that's when two objects collide and they move together as one. They stick together. Like a meteorite that hits the Earth. The meteor is moving down further in the Earth, but they stay stuck together. Maybe some car crashes also. So in a perfectly inelastic collision, there is no bounce. Notice in picture 2 here, they stick together. The balls are stuck together. Only momentum is conserved. So elastic conserves everything and they bounce. Inelastic conserves only momentum and they still bounce. And perfectly inelastic, they stick together and only momentum is conserved. So if we see here, we have a perfectly inelastic collision, which right away, once we start getting good at this, tells us the cars are going to stick together. In this case, this car is going much faster, so they'll still move, but they're going to move in this direction when they're stuck together because car 1 here had so much more momentum. So here's a nice little visual representation of each. In an elastic collision, here we see what they're going to look like. Well, both elastic and inelastic, we'll explain the difference, before they collide and after they collide. So they're going to bounce. That's the key that we're showing here. They bounce off each other. Remember, elastic would keep its shape. If we drew a better picture of inelastic, instead of a ball like that, we'd probably draw the ball kind of like that, so it changed its shape. So that would be a better picture for inelastic. But either way, with elastic and inelastic, they bounce. Perfectly inelastic, notice that afterwards they stick together. And this is the chart you kind of want to memorize. It tells the main differences between the two. Three types of collisions: elastic, kinetic energy, and momentum is conserved, and they don't stick together, they bounce. Inelastic, note, you can ignore this, kinetic energy is not conserved, momentum is, and they still bounce. And perfectly inelastic, kinetic is not again, momentum is, and they do not bounce, they stick together. So really, you don't need to remember momentum. Everything conserves momentum. All you need to know is elastic is the only one that conserves kinetic, because it's you can think of it as bouncy and stretchy. Inelastic still bounces, and the only thing that won't bounce at all is perfect. It's perfectly inelastic because they stick together. Go ahead and add that to your note guide, and we are done.